All right, second part of hypothesis testing. We'll talk about critical regions and critical values. Okay, so let's say we have an alternative hypothesis that the proportion is not equal to 0.2. That's what we would call a two-tailed test. Our two tails, let's also say that we have a significance level of alpha equals 0.05, so a 5% significance level. Since we have an alternative hypothesis that is not equals to, not a greater than, not a less than, but a not equals to, that means that our extreme values, our unusual values, are going to be in the far right or the far left. So if we take our alpha, like we were doing in the previous chapter, of 0.05 and dividing it by 2, then half of it is going to be on the far right, 0.025, and half will be on the far left, 0.025. Now remember, most of our values are going to occur in the middle of this section, the white section. So these values that are shaded in blue are the extreme values. We call those the critical regions. The two values where we change from the regular region, if you will, for now, to the critical region are called critical values. So in the last chapter, we spent a lot of time going back and forth from probabilities, 0.025, 0.975, and so forth, to the z-scores, using the normal distribution table, and back again. Given a z-score, what's the probability, what's the area under the curve? These are the same values. So if we calculate our z-scores with the 0.025 on the left and on the right, we'll get two z-values, 1.96 and another negative 1.96. These z-values that separate the critical regions from the rest of the graph are called critical values. Here's why these are so important. These critical regions, if our probabilities fall into these critical regions, we will reject the null hypothesis. Remember, the null hypothesis is the one with an equality in it. So if we have results that are too extreme, then we want to reject the null hypothesis. It would be lovely to say that we would accept the null hypothesis if we have values that are in the expected region. But we don't use the word accept the null hypothesis. Instead, we use the phrase fail to reject the null hypothesis. A great analogy to this, why we use fail to reject, is the court system. You are frequently either found guilty or not guilty, but simply because somebody is found not guilty does not mean that they are innocent. That's a different thing. So we don't accept the null hypothesis, we fail to reject the null hypothesis. Okay. Next idea. Let's say that we have a 0.05 significance level again, but we only have a right-tailed here, or left-tailed here, I'm sorry. The critical region is that one region on the far left-hand side, so those would be our extreme values, and they would correspond to a z-value of negative 1.645 for the critical value. Remember, the critical value separates the critical region, the region for rejection, from the rest of the region. And it's given by our significance level, 0.05. Don't forget, the rejection region is the critical region, and the rest of it is fail to reject, the null hypothesis. Okay, a left-tailed test. An example of a left-tailed test would be our null hypothesis is the proportion is less than a certain value, negative 1.25, let's say. So that when we graph this, we graph the null hypothesis. We're graphing a value that's less than, so on the left-hand side of negative 1.25. That would be a left-tailed test. A right-tailed test would be where we have a null hypothesis that is a greater than statement. So let's say the mean is greater than 1.25. So we would have the area here in the critical region to the right of 1.25. And a two-tailed test would be where our alternative hypothesis is not equals to. So it's not just a greater than, it's not just a less than, it's not equals to. And those would have extreme values on the far left and on the far right. So left-tailed, right-tailed, and two-tailed tests come from graphing the alternative hypothesis. And the area in the middle of those values, the white area for each of those, that's where the null hypothesis should be. Okay, let's do a quick example. Using a significance level of alpha equals 0.01, so a 1% significance level, find the critical z-value for this alternative hypothesis of p is greater than 0.5. Okay, so since it's a greater than for our alternative hypothesis, we have a right-tailed test. Don't forget that when we're finding this, we want to do the area to the left using our normal distribution table and finding that z critical value. So 1 minus 0.01, 1 minus alpha, gives us 0.99. And we get 2.33 for our critical value. Okay, notice we did not use the 0.5 from the alternative hypothesis to find the critical value. To find the critical value, we just use the significance level alpha. I'll say that one more time. To find the critical value, we only use the significance level alpha. Let's do another example. Let's use a significance level of alpha equals 0.10, so 10%, and find the critical z value for the alternative hypothesis H1 is P not equal to 0.5. So this is a two-tailed test because it's not equals to. There's a picture of the alternative hypothesis. And if we go to our normal distribution table, or if you're using your calculator and find the corresponding z values, 1.645. Don't forget again here, this is a two-tailed test, so we would have to take our alpha